Hello, Spencer. Hello, Kennedy. Let's see who else is here. Hello, Connor. Okay. And hello, Zane and Jared. Basically, we'll do projects during the lab. There is no time to postpone anymore. Thanks to those who initiated discussion. Sorry if I didn't reply in time, but we'll do things. Just plan on attending Wednesday night. We are looking on rotators in class, and last time I spent too much time on the introduction. If you are interested, you can re-watch it again. The quantum properties of rotational motion, for example, any diatomic molecule is rotating, or electron around nuclei is rotating, and there are associated quantum states. To describe rotational motion, we made an analogy between linear and motion on the circumference. And to parameterize motion on the circumference, one can take either arc length or angle, right? And then last thing that we did was to convert make an analogy between momentum, like linear momentum, which infinitesimally agrees with just momentum along circumference, and after cancellation through the polar coordinates, we got that angular momentum operator is just derivative over the angle. And now we need to utilize it. What can we expect today? The solution very similar to particle in the box for motion of the rotator along the full circle. It is like particle in the box with open end, with periodic boundary conditions. And then, if time allows, I will just show same images as you all have seen in the freshman chemistry one about SPD orbitals, and make comment how to connect what we are doing today and what we will do next. Okay, I'll try to rush over the slides quicker than usual if I can. And feel free to stop me if needed. And is it right that we have only 2 weeks in the semester? What? Yep. 2 weeks plus exam. So exam will be presentations. 2 weeks will be 4 academic lectures, 1 lecture when I'll share my vision how to write a report. And last meeting there will be peer review of your reports. Yes. What reports? Reports on the project that you haven't completed, and some didn't start, but it will be in 2 weeks, Friday of the next week. You bring them in class or send me the links. I'll share it, and we will during the class we will do reviews. And then during the scheduled exam time, whatever it is, we'll do presentations. Make sense? I do not see much enthusiasm and happiness. Okay, let's. I just booked on this. No, we'll do not just talk, we'll do projects during the Wednesday here. I just typed in this ugly handwriting stuff, steps of completing the projects, just 2 pages, and it is what we did. So motion on the circumference, and then we derived that measure of motion on the circle analogous to linear momentum is angular momentum. And due to transition between polar coordinates with radius and angle and linear coordinates, the angular momentum, which is cross product of distance from center to the linear momentum, will be derivative over the angle. I really like basic things of describing where this equation is coming from, but we spent like the whole Monday before Thanksgiving on it. So I'll skip the simple derivation discussion, but this is a vector that goes, in our case, it is only one z component, but generally angular momentum is a vector that is perpendicular to the plane of rotation, and its length is equal to the product of distance from center and linear momentum. But through simple derivations, it is equivalent to derivative of the, so here we should assume wave function, over the angle, over the rotation angle. So if we do quantum theory, we do need operators. So Hamiltonian, in the case of rotation, will be analogous to kinetic energy because there is no potential, right? So here are some quick tricks. The actual well-known momentum, well-known kinetic energy is linear momentum squared over two masses, right? Linear momentum squared over two masses. And here we do a trick. We multiply it by r squared in the numerator and divide by r squared in the denominator, right? No one can forgive me. And then we are renaming these components. So if linear momentum is perpendicular to the position of the rotating object and center of the circle, then cross product gives just like sign that appears there disappears, and you have just distance times linear momentum, right? And we define this product as angular momentum. Okay. The stuff here, mass times radius squared, will be an analog of mass for rotational motion. The meaning, philosophical meaning of mass is inertia. How much the object resists to attempt to make it move. So if you have either a very heavy wheel or it has like lead bullets put it on the edges, we need more energy to make it rotate. So this inertia in the denominator is how it resists to make it spinning and how it resists to make it to stop. And then the kinetic energy looks algebraically in the same form as kinetic energy for linear motion. The object corresponds to amount motion squared divided by inertia. Make sense? It was p squared over two masses, now it is L squared over two inertias. Next, the angular momentum looks very similar mathematically to linear momentum, minus I h bar, but instead of derivative over position, it is derivative over angle, right? Because if it is a rigid rotator, then distances are not changing, it just changes the angle, right? Squared over inertia. And then if we open brackets, it will be Planck constant squared to inertia and then second derivative. So absolutely the same as we had for electron in the free space and for the particle in the box, right? So mathematically, it's just second derivative and nothing else in the Hamiltonian. It should be quite easy to solve. Any questions online from Spencer, Kennedy, and Connor? Questions one, questions two, questions three. Spencer, if you're speaking, I don't know why it doesn't come through. If you have a question, please type it. If no, I'll return and go with the slides. I wasn't asking a question, but thanks. Okay. Thank you. Okay. And as we do typical practice, as we were doing typical practice, if you do have Hamiltonian, we need to find it eigenstates and eigenvalues. Right? So there was a little benefit in our effort to waste time on commutation. It was not only drying our brains, but we may get a little benefits right now. So let me remind what we were observing. If we compute any quantum operator and any integer power of it, like momentum and momentum squared, or momentum and momentum cubed, or whatever, the commutation will be zero, right? Because it will be like if momentum and momentum squared is p, pp minus pp, p, which will be ppv minus ppv. I hope it is quite convincing. Another thing, if the operators compute, if swapping of the operators does not give something except zero, then they share the same set of eigenstates, eigenfunctions. So if we solve for eigenfunctions of, I think we were doing it like for momentum and then kinetic energy, momentum squared for the free space, they both had the same set of eigenfunctions, plane waves, right? We are going to practice the same thing here. So general property, if you have angular momentum squared will be zero, Hamiltonian contains only angular momentum, therefore there is a shortcut. If you find eigenstates of z projection of angular momentum, then you automatically find the eigenstates of Hamiltonian. Make sense? Are there any confusion questions why there is a letter Z? Well, better ask now, because after one starts writing long formulas with many notations. So just we repeat. Angular momentum is a vector because things may rotate in different planes. And it has only LZ component if objects are rotating XY plane. Then vector of angular momentum protrudes only in Z direction. But generally, it is a three-dimensional vector that may have four components, like X, Y, and Z. So, unknown wave function, and I apologize for this confusing notation, psi of phi. So we have angular momentum operator, we have unknown wave function, we have unknown eigenvalues, and we have unknown wave function, which if we divide left and right part, there is a common notation to use the letter m for eigenvalue of angular momentum, and the reason for letter m, you even may suggest why it is. Are there any quick thoughts? So if electron is moving on a circular orbit or on a circular coil, what happens around? As a result of motion of charge on the circular orbit, what appears in a vacuum around? It's like high school physics. Oh, I see someone is giving. I know it delays our progress through the slide, but I think there is no reason to go if we miss some intermediate things. So, physics in 2 minutes. What happens to the charges?
Repel.
Repel or attract if they are opposite sign?
Opposite sign is attract.
Okay. What happens to the coils with current?
Creates magnetic field.
Okay, and then 2 coils also can attract or repel, right? Depending on. So, if there is even one electron moving in a circular orbit, it's like a current on a coil. So it creates
magnetic field.
Magnetic field starts with which letter?
M.
Okay, so therefore we have letter M here. Make sense? And in the freshman chemistry, when you are looking on SPD orbitals, you know it's not a secret, like principal N, L, M, S. Principal, orbital, magnetic, and spin quantum numbers. So letter M stands for magnetic. And it differs from dimension of angular momentum by Planck constant. Basically, Planck constant has dimension of angular momentum, and M is integer. So it is done in order to make this thing dimensionless. So I have no doubts that each of us can solve it. So first derivative of unknown function equals constant times unknown function. We can put everything that relates to unknown function on the left. So increment divided by unknown function, and everything which relates to independent variable on the right. And then if we integrate left and right part, on the left, integral of t psi over psi will be logarithm, right? And on the right, it will be imaginary unit, magnetic number, independent argument, which is angle. And then if we put it into the power of exponential, we are going to get constant and then exponential with imaginary angle. Right? So Euler formula, same as plane wave. And solutions will have this shape. But when we were speaking about particle in the box, the question was the same, but what did we do after getting the general solution? Like in differential equation, solutions can be general and
we found the constant.
Right. This is general solution, and summation of general solutions will be solution as well. So we need to find such summation of general solutions that will match something, either initial condition or boundary condition. When it was particle in the box, there were infinite boundaries. What are the boundaries here? Like if it rotating electron or diatomic molecule makes a full circle.
Radius?
No, it doesn't. Yes?
Angle?
Yes, the angle is independent variable. When it makes full circle, 2 pi, what happens next?
Starts over.
It either starts over, or if we are very rigorous, we can go that it will go over 2 pi, right? And then accumulating 2 pi, 4 pi, 6 pi, like a continuous variable. But value of function f after the full cycle should coincide with itself. It's like a snake eating its own tail, right? So instead of boundary, well, it is a strange boundary. It's boundary with itself. And in some sense, it's called periodic boundary, because after the period, after 2 pi, it will be the same stuff. Make sense? So it was the boundary conditions for particle in the box. Here is a boundary condition for rotation. So wave function after it makes full cycle 2 pi should be the same as without making this full cycle. So wave function at angle equals the wave function at angle plus 2 pi. And if you plug this condition into general solution, we'll get if there are any restrictions. Another thing that we need to take into account is normalization, right? So wave function square should be 1. The conjugation swaps the sign, which means just integral of the independent variable qubit 2 pi. So unknown coefficient square is 2 pi. Then wave function will be 1 over square root of 2 pi and this quantum number. Exponential is I, magnetic number, and angle. So if we want to match the condition of this snake eating its own tail, right? Then we have this condition. So you can cancel out the normalization, although we spend a minute to get it. And then the wave function or exponential to the imaginary power of magnetic number phi cancels, right? And then we have a condition that I to pi times m in the power of exponential should give 1, right? So 2 pi comes from boundary conditions, m comes from the general solution of this differential equation. Now, which values of m will serve as solution to this equation? Like what if I take m equals 1/2? What will happen? I pi e to the power I pi, or what it is? So here is like x, y, phi goes here, and if you have a radius of could be real and imaginary. So if angle is 0, then this number will be real will be 1, imaginary will be 0, right? 1, 0. If angle equals pi over 2, then real equals 0, 0, imaginary equals plus 1. If angle equals pi, then real equals -1, imaginary equals 0. So if you plug in m equals 1/2, then it will be -1, which is not good. if you put plus or minus pi over 2, it will be imaginary. And if you have m equals 0, 1, 2, then it makes the full cycle, and it will be again 1, 0, real part. So what will be the answer for the n?
0 over 2.
And minus
1 over 2.
0 plus minus 1 plus minus 2, right? Integer number of full cycles. Just in case you do not feel convinced, maybe you already do. It is my Euler function is cosine and imaginary sine. The imaginary part is 0, real part is 1, and then one can expand this equation onto two equations. 1 equals cosine 2 pi m, 0 equals sine 2 pi m. And if one draws these two lines, there will be simultaneously matching this condition at 0, at full cycle, at two full cycles, right? So one is writing it as m equals 0 plus minus 1 plus minus 2. I'm going to quickly check if there are any questions online. Feel free to stop me if there are any confusions. More questions. Questions 1, questions 2, questions 3. I'm going to continue. Okay, we may want to interpret this stuff. So maybe when I was trying to play music, it conflicted with sound line. So integer value on the number is beautiful because it repeats the same structure. So let's try to interpret and analyze this solution in the same way as we were interpreting the solutions of harmonic oscillator. Just try to take home, make a take-home message out of it. So if we, no, it's not like harmonic oscillator, it's something unique. Maybe as we were analyzing density of states, like just browsing the space of private states. So magnetic quantum number, which is angular momentum divided by a constant, will be on x-axis. And you know that solutions will be plus minus integer. Then on the y, we can put the energy, which is matrix element in the sandwich between eigenstates. So for the bra and cat angular brackets with m inside, I take it as a notation for this eigenstate. Like angular bracket of m will be same as here. And then if we plug in operator of total energy between the sandwich and practice operator includes second derivative, then by taking second derivative of the exponential twice, it will come up front, and and then the function will cancel each other. So the energy of rotations will be logarithmic quantum number squared over inertia. So if you look similar to parabola, but discrete parabola, okay? Only specific values are allowed. And here is an interesting observation. The same value of energy except zero can be obtained by rotation with the same absolute value but opposite direction. So if it rotates forwards with speed or angular speed +1 and backwards with angular speed -1, the kinetic energy of rotation will be the same. So the appropriate word for this phenomenon is degeneracy. It is the same energy appears from different values of quantum numbers. And in real life, it happens often with many systems. Like before, we typically had one energy, one state. When we analyzed 2- and 3-dimensional particle in the box, it was not literal degeneracy, but it was similar energy in a stripe, right? And here it's a literal one. So the solution that I offered you and we were considering is not wrong, but it is incomplete if we speak about realistic systems. So we need the solution because of beauty of the simple solution. Simplicity. If it is a real 3-dimensional object that can rotate in not only in x-y plane but in other planes, then this solution will be modified. So I want to save time and effort and do not dry your minds because more rigorous solution, which is qualitatively similar, but it takes more money. If we take into account 3-dimensional data, which means we allow this dynamic mode to change plane rotation, then there will be not one magnetic quantum number, but two quantum numbers. L, which will control total value of angular momentum, and then M. So the eigenstates will be parameterized by two quantum numbers. And if you care practice is the same thing, then the energy will be determined by not by literal square, but L times L plus 1. There is a way to derive it, but it is not in the remaining 2 weeks before the end of the course. And a relation between angular and magnetic quantum number is that M is smaller than L and bigger than minus L. And L takes only positive values, 0, 1, 2. So for L equals 0, M also equals 0. For L equals 1, M takes 3 values. Minus 1, 0, 1. For L equals 2, magnetic takes 5 values. Minus 2, minus 1, 0, 1, plus 2. For L equals 3, it will be 7 values. And if you place this solution in the same diagram, we can speak, we can describe it on the language of degeneracy. The higher the energy, the larger number of the states that provide the same energy. So for lower state, it will be only 1. For first state, rotational state, it will be 3 degeneracy. Here 5, next 7. And one can write a simple equation to match it with equation that will give values 1, 3, 5, 7. So like 2, L plus 1, right? These rotations are literally connected with hydrogen atom. They are related to this, one call them spherical functions, because instead of polar coordinates, those are spherical. And additional feature comes from the fact that one takes into account rotation in the plane perpendicular to our main magnetic rotation. So one calls it this angle theta, and the absolute value, real parts of the wave function will look like flowers with center, and then it will be function of two angles. So depending on the values of these quantum numbers, it will take different shapes. So interpretation is as follows. If by inspecting this function along certain angle, we have a homogeneous picture, this purple doesn't change, it means there is no motion, there is no magnetic motion. You can say that magnetic quantum number is zero. If we go along this line, along this angle, and we see it changes from positive to negative and back to positive and has nodal points, we call it zeros, it means there is substantial motion moving this rotation out of plane. And in some sense, number of nodes and amount of angular motion are correlated. So basically, by looking on the image, one can say what would be the quantum numbers. Like 4, L equals 4, phi equals 0 for this one. And then one can practice the same thing. So if one looks over all solutions, then they will have the same energy, but there will be several degenerate solutions. Next one in the set will have nodal points along phi, which means it moves on the magnetic circumferences. And number of nodal points along theta will be less. And if one progresses forward, one can identify in which direction it moves more vividly. So there is the larger number of these lobes and nodes, the more is rotation. So this example shows no rotation along theta, and all motions goes along phi. So several full cycles, and here are these orbitals as they look like, that you probably have seen in the freshman chemistry. So S degeneracy, no degeneracy, P dumbbell degeneracy 3, D degeneracy 5, and the next is F and G. I don't know if there is any here. I think it is stuff in the YouTube that shows the same solutions in the visual form. And I brought it here because you can see the larger the number of these petals, the quicker it moves. So there's this idea about angular quantum number being bigger. So one can make a table and put the degeneracy and energy into the table, and then this information can be used to interpret rotation effect. I think we should return to this subject next time and speak about it a little bit more. John is not in the class, it was for previous year. And I think it is time to announce completion of the meeting. Thank you for your questions, and let's plan on doing fantastic effort on Wednesday night. Okay, I am going to check if there are any questions, and if there are, please ask. If there are no, feel free to depart. Even then, I'm going to disconnect. Kennedy, if you want to speak, let me know, and we can speak right now or set up another meeting.
Thank you.
Thank you.